second talk of today. So our next speaker is Dr. Sam van Leuven. Sam is a postdoc at the moment at Leeds University, and the title of his talk is Towards Holography for non-AdS spacetimes via long-string phenomena.
Good. Thanks, Robert and the organizers, for giving me the opportunity to talk. Let me also, in advance, apologize to some of my colleagues at WITS who have already seen this talk in a somewhat different format. So I think the title of my talk is Towards Holography for non-AdS spacetimes via the long-string phenomenon. It's based on work with my PhD supervisor, Erik Verlinde, and another PhD of his, Magnus Visser, and also on some work in progress. So the talk will be very conceptual in nature, as the paper is. So many of the details have to be made more precise, but I hope you can bear with me. So let me start by reminding you of the holographic principle, which states that for any theory of quantum gravity in some volume V, the number of degrees of freedom involved in its description should be bounded by the area of the boundary surface in Planckian units. I will refer to this boundary surface as a holographic string in the remainder of this talk. Also, if this holographic description is quantum mechanical, then you can precisely think of n as the logarithm of the dimension of its Hilbert space. And I will abbreviate holographic quantum system in the following by H, Q, QS. So, as you all well know, AdS-CFT realizes the holographic principle. So AdS you can think about as some volume in which we have a theory of quantum gravity, string theory. And the statement of AdS-CFT is that the holographic description of this string theory can be thought of as a CFT that lives on the boundary of this volume. So I've drawn here the Poincare time slice of the Poincare patch of AdS, and then S of 0 denotes the asymptotic boundary. But the holographic principle is more stronger than this. It states that for any volume, for a theory of quantum gravity in any volume V, there should be some holographic description with the number of degrees of freedom scaling as the area. And AdS-CFT gives a precise way how to think of this holographic quantum system for interior volumes. Namely, it's obtained by some coarse-graining transformation of the boundary field theory, where you essentially coarse-grain over coordinate size cells of size rho, and you integrate out all modes with smaller wavelengths than this particular cell. Right. So one important aspect of the AdS-CFT correspondence that sort of follows from this perspective is the UV-IR correspondence, which states that large distances in the Bogue, the IR in the Bogue theory, corresponds to the UV, the high energy in the CFT. And vice versa, so small distances in the Bogue correspond to IR in the CFT. Finally, in global AdS, which you can think of as a solid cylinder, there's a fundamental IR cutoff on this holographic renormalization point of view at the AdS scale. And essentially the reason for this is that the holographic dictionary tells us that the central charge of the CFT scales as the area of the Bogue surface at the AdS scale in Planckian units, which means that in the holographic renormalization in global AdS means that as you go into the Bogue, as you renormalize into the Bogue, the moment at which you reach the AdS scale, essentially the coarse draining cell has become as large as the sphere in which the CFT is defined. So at that point, in other words, the UV cutoff has become the IR cutoff, and it's not obvious how to continue deeper into the book to sub-AdS scales. So to say it strongly, holographic renormalization in global AdS at least appears to break down at the AdS scale. So the goal of our work was to study some features, some general features of the holographic quantum system that would be relevant for sub-AdS scales. So how to think of that system, and in particular, is there a sub-AdS analog of holographic renormalization? In other words, is there some procedure that we can apply to the holographic quantum system to obtain the system that corresponds to interior volumes at sub-AdS scales? A related question to that is what happens with the UV-IR relation of AdS-CFT at sub-AdS scales? In particular, is it still true that as you move deeper into the sub-AdS, you're still going to the IR of, that's still in the IR direction of the holographic quantum system. And another question which you might expect could be related to these questions is what are the implications for holographic descriptions of Minkowski and the Sitter space? Essentially because at sub-AdS scales, the negative curvature of AdS becomes negligible. And yeah, so it might mean that lessons about the holographic quantum system and sub-AdS scales could have implications. Static patches. So some important clues that I want you to keep in mind is that large AdS black holes with horizons radius larger than the AdS radius, they have a positive specific heat, and this is also natural from the holographic description because of this UV-IR correspondence, which states, so positive specific heat means that if you decrease the size of a black hole, it cools down, and that's consistent with the idea that as you probe deeper into the bulk, you reach the IR of the holographic quantum system, CFT. Now, on the other hand, small AdS black holes have a negative specific heat, and as a matter of fact, also asymptotically flat and the Sitter black holes. So this is so in particular these black holes, they heat up as you make them smaller. So this is not very natural from a point of view, of a Wilsonian point of view on field theory as being the holographic quantum system. Another clue, some small clue, is that if you compare the GTT component for AdS or DS static batch, then in AdS there's a blue shift towards large distances, which is consistent with this UV-IR correspondence. But for the Sitter static batch, there's in fact a red shift. So these latter 2 points, they might interpret them as suggesting that large distances in the bulk, or the IR in the bulk, should perhaps correspond to the IR of the holographic quantum system. In other words, it might be that this UV-IR relation that we know of AdS-CFT does not apply to holographic descriptions of these other space-times. So I've illustrated that in the lower 2 figures, where again you see the Poincaré batch of AdS, and now also the time slice of the static batch of the Sitter, where large distances would correspond to the IR of the holographic quantum system. So the main motivation of this talk is is to provide some evidence and some way of microscopic realization of such a reversal of the UV-IR correspondence for non-AdS spacetime. So with non-AdS, what I mean precisely in this talk is sub-AdS Minkowski space and the static Petrov de Sitter. Those will be the spacetimes of interest. All right. Any questions?
Maybe I missed it. You're talking about pure gravity here, or is it general? Does alpha prime play a role?
No, I will assume that we're in some limit that we can talk of something that's pure gravity without conjecture.
Alpha prime is small.
Yeah.
So, for the small black hole, negative specific heat of small black hole, is the field theoretic way of understanding why this black hole would have small negative specific heat?
So yeah, there will be one expert coming to this conference, David Mandelstam. Sadly, he's not here yet. He has done some work on that, on understanding this from a field theory perspective. There are also another group that works on that, at least one other group. I will comment on it in the conclusion, but I think it's fair to say that that is inconclusive as of yet. It's not properly understood. It's still an open question on how to interpret this. Yeah.
What's the other group that works?
So there's, I think it's more a numerical group. It's Hanada is part of it, and Jonathan Maltz, Ethan Berkovich, yeah, well, I will get back to
like
that.
The temperature of the small black hole, should it be interpreted as the temperature of the boundary theory or not? That's the question, because it is not a thermodynamically dominant solution.
Yeah, so you're saying it's not a stable position.
Thermodynamically.
It's not an equilibrium.
Yes.
Yeah, so there are ways to
Yeah.
Okay. I will make a small comment. All right, so this is the overview. So I will introduce now the holographic quantities that we will use to study these non-AdS spacetimes and the specific conjecture. So these non-AdS spacetimes are all that we consider are all static and spherically symmetric. We'll take the holographic screens labeled by some radius r to be spherical and centered at the origin. So here's the illustration of such a screen in global AdS. And so more invariantly, you can think of it as the maximum area slice of a causal diamond. But for us, it's just simple spherical screens. All right, so the three properties of this holographic quantum system on a screen as of R I will focus on are the number of degrees of freedom in the system. I call it UV degrees of freedom because as in AdS CFT, we will think of this radius as a UV cutoff on the quantum system. So in particular, C of R is just the area of the screen in Planckian units. Epsilon of R will be the UV cutoff on the system. And we'll also consider N R sub R being the total energy in the system in units of epsilon of R. From now on, I will frequently drop the subscript R. But you should keep in mind that we will always think of a family of holographic quantum systems labeled by such a radial group. So these quantities were already considered by Susskind and Witten in the context of AdS CFT. So in their paper, they introduced a small distance cutoff delta on the CFT, which is related to this epsilon. And then this small distance cutoff by UV-IR corresponds to the large distance cutoff in the bulk. You see the familiar relation between energy scale in the bulk and energy scale of CFT and radial movement in the bulk. So upon introducing this UV cutoff, you can actually do counting of the number of degrees of freedom in the system if you assume that to each cell or lattice site you associate proportional to the central charge number of degrees of freedom. You simply multiply the central charge by the volume of the lattice, and using the holographic dictionary, this gives you that the number of degrees of freedom is precisely proportional or it's precisely consistent with the holographic principle. It scales with the area of the bow surface in Planckian units. So this was actually the first paper in which it was made clear that AdS-CFT is a realization of the holographic principle. Furthermore, they also remarked that putting this system at a temperature of the order of the UV cutoff creates a black hole of radius r log. So in that sense, we can also think of epsilon as the typical excitation energy per UV degree of freedom in the maximally excited state, which is the black hole. There is no, that's the excited state. Finally, in the case that we're in the black hole state, then n is equal to c, obviously, and as such it counts the number of UV degrees of freedom. So a further illustration of these quantities I'll give in context of AdS-CFT2, which will also be important later on. So in the case of AdS-CFT2, the holographic dictionary is as follows. The central charge is given, wrote it in a particular way to emphasize the area of the work surface. It's given as follows, and the scaling dimension of the CFT is related to the energy of the bow. And then our quantities, capital C and capital N, are related to the central charge by these simple factors. So in particular, what you see is that N is essentially sort of counting where delta is counting the number of IR excitations, counting it's quantized in units of 1 over L. N is quantized in units of 1 over R, UV cutoff. So the Cardi formula can also be expressed in terms of C and N. And well, the advantage of C and N is that they refer more directly to the holographic quantum system on the screen that we look at. So it turns out that C epsilon and N admit definitions in terms of the local geometry around this screen. So for C, you know that's just the number of degrees of freedom, which is the area of the screen S in Planckian units. So that only depends on the metric restricted to S. And there appear to exist similar definitions for N and in terms of the metric, whereas epsilon will depend on a derivative of the metric. I will not go into these definitions that do appear in our paper, because ultimately I think the precise definitions are not that important. However, they motivate a conjecture, which is the following, and which will be central to the rest of our story. That is that the holographic quantum systems on two screens, S and S tilde, in two geometries, G and G tilde, have the same number of excited degrees of freedom if the metrics are identical on the holographic screens, S and S tilde. So in formulas, this is the statement that if G restricted to S is equal to G tilde restricted to S tilde, and the Planckian units in both spaces agree, then the number of degrees of freedom in the associated holographic quantum systems are the same. This is nothing more than the holographic principle. But in addition to that, conjecture that also the number of excited, the number of UV excitations is equal. Now, as I said, this epsilon depends, actually, its geometric definition appears to depend on a derivative of the metric. So in general, this will not be sufficient for the UV cutoffs to be the same. But in our examples, they will differ by some order 1 constant. So we'll add to the conjecture that these things also should agree in the holographic quantum systems. So that's the conjecture, and then the idea is to use known features, these known features of some holographic quantum system on S tilde and G tilde, to study those same features in a different geometry for which we a priori didn't have a good idea on what they are. And in fact, as I already said, we want to know if there's some analog of holographic renormalization in these non-AdS spacetimes. That means we want to study a family and how numbers are related. And in that case, there is a very convenient way to study a family of screens S in a geometry G via some G tilde if G and G tilde are related by a conformal factor. So let me explain that. So suppose that G and G tilde are well equivalent, then the scale factor is a constant if the screens are spherical, which we assume, and if omega only depends on the radial coordinate. So in that case, the geometry G restricted to the holographic screen S can also be found. So I denote the image of S in the rescaled geometry also by S. So this screen can also be found in a constantly rescaled G tilde geometry. And so that's what I'm saying. So any S in G is contained in this constantly rescaled geometry, G tilde, and then the foliation of G in screens S is given by taking one screen in a family of constantly rescaled spacetimes. So the schematic picture is here. So on the horizontal axis we have foliation of G tilde, the geometry G tilde, in screens S tilde. And on the vertical axis we have this conformal factor. So each horizontal line in this graph corresponds to a constant rescaling of the G tilde geometry. And then we think of G as sort of a diagonal in this family, where in each constantly rescaled geometry we pick a single screen corresponding to the conformal factor to foliate G. So we have mapped the effect is that we have mapped a foliation of G in screens S onto a set of screens in a family of constantly rescaled spacetimes. And then in that case, our conjecture that if the metrics agree on a specific holographic screen, then these holographic quantities should be equal. So the conjecture in this particular case reduces to this statement. So yeah, if you guys already said this. So the advantage of this is that if the holographic quantum system of G tilde is a CFT, if we understand it, then this the holographic interpretation of a constant rescaling is not difficult. It's just a rescaling of the central charge. So, all right, maybe this is a bit too abstract for what. So let me get to the examples. So the specific examples of wild equivalent spacetimes that we want to consider is, well, on the left-hand side we have the geometries of interest. So we have sub-AdS D, we have Minkowski, and we have the static patch of de Sitter. And it turns out that these geometries, if we add a transversal circle to them, they are wild equivalent to all locally AdS-free spacetimes times the d-2 sphere. So here you see AdS-D is just wild equivalent to the global AdS-free, whereas Minkowski is wild equivalent to the massless BTC, and the de Sitter static patch is wild equivalent to the Hawking page BTC. So it's a sketchy way to think about the map is that you just choose a conformal factor that rescales the SD-2 in AdS-D to constant size. This affects the circle precisely in such a way that it's fibered over the radial direction to form an AdS-free. But clearly, when the SD-2 shrinks, the S1 will blow up, and vice versa. So in formulas, it's just this. So on the upper line, you see for kappa equal to -1, 0, or +1, you'll see the metric of global AdS, Minkowski, and the de Sitter static patch, respectively. And if we multiply it by this simple Weil factor, the locally AdS-free matrix, and we invert the radii, the radial coordinates are related by this inversion, then you have this Weil equivalence. Now,
maybe I missed. So you added this extra S1.
Yes.
So are you saying you're restricting the theories that have some global U1 symmetry by doing that, or is there some physical understanding of why?
Yeah, I'll get to that also in the conclusion. But indeed, you have to, if you want to find a concrete string theory embedding sig, you need to isolate some S1 in some way, and I'll make a comment also.
But this S1 could be an S1 inside the S5.
Yeah,
say.
exactly.
So you're working here in global coordinates everywhere? You're working here in global coordinates everywhere?
Yes. All right. So the upshot of this is that we can relate the upshot of the inversion of the radius is that we can relate that sub-AdS D screens are related to super AdS-free screens, and that's exactly what I was saying. That we want to use the known holographic description of some G tilde geometry, which in this case for super AdS-free is known, to study, to probe screens at sub-AdS, at which we do not have good control. Finally, I will take the transversal circle to be smaller than the AS radius. So this n is over L is much greater than 1. This will affect the AdS-free geometry here by putting a conical defect in the angular coordinate in AdS-free. All right, so let me return before going to more microscopic interpretation. Let me return to the consequence of the conjecture for this specific example, for these specific examples, so the conjecture states that these quantities should agree for the holographic quantities on the one hand on this sub-AdS or DS, these quantities should agree for the holographic quantum systems that live on the one hand on the sub-AdS and on the other hand on the equivalent screen that sits in a constantly rescaled locally AdS-free space-time. So how to think of this? Well, let's glue these space-times for some small value of R0. Let's glue them along their equal screens. So here you see the Penrose diagrams of AdS-D cross S1 and AdS-D cross SD-2, and we glue them along this screen at R0. And similarly, for the Penrose diagrams of the static patch, the sitter, the exterior of the BTZ black hole. And now imagine that you increase the size of R0 so that you're sort of slowly building up sub-AdS or sub-DS. Then what happens from the AdS-free perspective is that we are adding degrees of freedom, essentially, because the prefactor is growing and the prefactor is just the central charge. We'll make this more precise later on, but this is essentially what's happening. We're adding degrees of freedom, but the energy of those degrees of freedom is decreasing because as you make R0 larger, because of the inversion of radius, we are moving towards the IR in AdS-free, moving into the bucket. All right, so I'm claiming that this has the potential to provide some framework of understanding this IR correspondence for sub-AdS-D. But let me now try to make that a little bit more precise. Any questions so far? So once more, let's look at sub-AdS-D and recall that the screens S sub R0 for the specific value of R0 in a constantly rescaled locally AdS-free space-time, they foliate sub-AdS-D if we let R0 run from 0 to L. Okay, so let's start with R0 being equal to L. That is, we want to consider the holographic quantum system in AdS-D at the AdS scale. So then we know that the number of degrees of freedom in that system should just be proportional to the central charge, which is given by the following. And moreover, we know that the UV cutoff of the system at the AdS scale is like goes like 1 over L, and the number of excitations is essentially 0. This is the negative vacuum energy of the antipacific. So this is something we know, and it will be useful to see how this is reproduced from the AdS-free CO2 perspective, because that will allow me to generalize this to sub-AdS. So for that, I write the upper metric with conformal factor, in this case equal to 1, because we take R0, at this point we take R0 equal to L. So there's just this AdS-free metric. And then I rewrite it in the following way. So I rewrite it yet in another way as the multiplication of the factor n squared by this metric in brackets. And I would like to think of this metric in brackets that has a smaller AdS radius, and in addition a conical defect in the GTT component, I want to think of this metric essentially as being dual to a seed CFT. This factor of n, then if we keep the Planck's constant in d+1 dimensions fixed, then this prefactor n, I would like to think of it as rescaling the seed central charge. You can easily see that that should be accompanied by a power d-1. So the way to see that is essentially that the prefactor blows up the small AdS3 space to a larger AdS radius with n of these copies essentially, and the factor n squared also multiplies the transversal sphere, so that guy is also blown up to size L. So that's how the power d-1 arises, right? So at this stage, we have want to think of this multiplication of the seed metric as giving rise to a symmetric product CFT, whose central charge at this point scales with the AdSD volume. And also the excitation energies of these seed CFTs, they're quantized in a smaller circle, so these excitation energies behave like 1 over small l. So this is not yet consistent with what we would expect for AdSD at the AdS scale. However, we should take into account the conical defect still. So the effect of this conical defect is can be understood in terms of a covering space theory. So we go to the covering space of the conical defect spacetime, and then the field theory dual to that has a Virasoro symmetry with a reduced central charge and a fractionated spectrum. You can find it by doing essentially looking at the Zn invariant part of the Virasoro algebra, and this is at the symmetric orbital point. This can be understood as the long string phenomenon, in which multiple copies of the seed CFT are glued together into a single longer degree of freedom by a twist operator. And you can see that would reduce the central charge because you're gluing together separate degrees of freedom into one single longer degree of freedom. And it will also have the effect that the spectrum becomes more dense because you have you're quantizing the theory on a much larger circle. So taking this conical defect into account then gives the correct number of degrees of freedom from the CFT from the AdS3 point of view. So the long string central charge reproduces the number of degrees of freedom that we expect for AdSD at the AdS radius. And moreover, this excitation energy of the degrees of freedom is reduced by factor 1 over n, which is also consistent with what we expect for AdSD. So the statement is that from the AdS3 point of view, we want to think of the holographic quantum system at the AdS scale as sort of n to the d-2 of these long string degrees of freedom. So the usefulness of this perspective is that we can generalize it to sub-AdS. So for sub-AdS, we know that we should take a particular screen in the constantly rescaled upper geometry, and this metric can now be rewritten as in the previous case. It can be rewritten into two ways. So the lower metric is the analogous metric as we've seen before. So we have this seed metric within brackets that's multiplied now by a smaller factor. And I also write an intermediate metric which has a larger AdS radius and which has which is not multiplied by any conformal factor. So we'll focus on these latter two metrics. So we claim that the analogous thing goes through. So in this case, we have the seed metric multiplied by some factor k, r0 over small l. This gives rise to, again, to sort of a larger central charge, k to the d-1 times this seed central charge, which can be thought of in an analogous way as the previous case. And now, again, we have to take into account the conical defect. In this case, going to the covering space does not fully resolve the conical defect, and that's because we still have a fractional fraction appearing in the GTT components. So if we do this partial long string phenomenon, you'll get a reduced central charge, again, in a fractionated spectrum. And this will this reproduces the holographic quantities that you would expect for ADS, sub-ADSD. So in particular, the effective number of degrees of freedom in this system is given by A R0 in Planckian units. Furthermore, because the spectrum fractionates with a factor k, one expects the excitation energies of these degrees of freedom to be larger than the long strings, in this case 1 over R0. And finally, the number of excitations in this system, one can verify that there is still, from the CFT2 point of view, there's still a twist operator present, which was also reflected in the upper metric. So that the conformal dimensions here are that of the twist operator. So we propose that the holographic degrees of freedom from this ADS3 point of view, that sub-ADS scales should be thought of as fractional strings, that is, strings that do not yet close onto themselves because of the presence of this twist operator. If you would fully resolve the conical defect, you would instead get the following quantities, but our claim essentially is that these long string degrees of freedom do not really fit at sub-ADS scales, and rather at sub-ADS scales we only see a fraction of the long strings, which are these fractional strings. So the important point of this is, let me summarize that in the following slide. So the idea of this is that from the ADS3 point of view, the microscopic realization of this expected IR correspondence is that as you go to large distances in sub-ADS, you are adding degrees of freedom by taking a larger symmetric product theory. However, the typical excitation energy of those degrees of freedom decreases because of the long string phenomenon. So that should be, we propose that could be a microscopic mechanism underlying an IR correspondence, similarly as that holographic renormalization is the microscopic mechanism that underlies a UV-IR correspondence. And this, well, as we already noticed, this is consistent with the negative specific heat of small AdS black holes. Furthermore, so I've only talked about sub-AdS until this moment, but we can do a similar analysis for the de Sitter static patch. So it's already given in the examples that the de Sitter static patch is well equivalent to the Hawking page BTC. In particular, the horizon of the static patch maps into the BTC horizon. And taking our conjecture again and following essentially through the same steps gives us that we can think of the sitter as essentially, in terms of the CFT2, as essentially the same CFT2 description. However, now there are excitations. We're not in a vacuum, but we're in a state with a specific conformal dimension, namely that conformal dimension of the Hawking page BTZ. So we like to think of that the holographic degrees of freedom of sub-AdS in this AdS-free language are long strings at some temperature, which should be the sitter temperature.
Sorry, just a clarification. How should I picture the sitter here, and what is the sitter?
So the sitter is the upper metric.
Okay.
It's the static patch. So it's let's see. Here again. Yeah. So the Penrose diagram of global de Sitter is like this, where you have these slices denote S SE-1 for the Sitter. We have the North Pole. This is essentially the North Pole. Here's the South Pole, and then the static patch would be the description of this patch. As seen essentially, the space is seen as from the viewpoint of a single observer at the North Pole. So, in particular, the static patch has a static metric, and the horizon is always at a constant distance of the size of the de Sitter radius. And similarly to the fact that we can consider sub-AdS by going to this fractional string perspective, we can also go to sub-DS distances, so the distances closer to the observer's world line away from the horizon, and we can verify that we should think of the holographic quantum system that lives on holographic strings at sub-de Sitter distances should be thought of as fractional strings at the same temperature, meaning that they are not fully excited yet and do not create a horizon. That's the factor of k over n squared, which is so for so you can use you can apply the Cartes formula to this particular CFT state, and then for R0 equal to L, this ladder factor disappears, and you see that you reproduce the sitter entropy, which ultimately is not, I mean, this perhaps a bit trivial because we just mapped screens onto each other and kept Planck's constant fixed. So the fact that the metrics are equivalent when restricted to the specific holographic screen and the Planck's units are equal implies that this area entropy. Okay. Finally, this proposal also identifies the vacuum energy in anti-de Sitter or the Sitter space with certain things in the AdS-free perspective. In particular, the AdS vacuum energy corresponds to the Casimir energy in the CFT2. And the Sitter vacuum energy would correspond to the energy of the excited CFT2 state. And that, we can check that this vacuum energy of anti-de Sitter or the Sitter is precisely reproduced by either the Casimir energy or the energy of the excited state from the CFT2 perspective. And in that sense, it appears that the long strings provide a naturally small value for this vacuum. All right, so let me conclude by giving some outlook. So first of all, it would be interesting to find a more explicit string theory embedding. So in fact, Vishnu has done some work where they studied the near horizon limit of intersecting giant gravitons. Those in AdS5 crosses 5, those gravitons or branes intersect over an S1. So this would give you a way to isolate an AdS5 cross S1 factor. It is also observed that in the near horizon limit of these black holes on AdS3 cross S3 geometry emerges. So it might be useful to try to understand if this sort of general story can be analyzed in more precise detail in this setup. There are also more general conformal equivalences. So you can have AdS-M cross Sn while equivalent to AdS-M cross Sm. That's studied by Balasubramanian and Naqvi. That would be interesting to study. I must say that is not that simple, not such a simple conformal equivalence as the one that we are using, that would require a -2 in the dimensions. Now, there was also a question about the negative specific heat. So that's also been studied by other groups. And essentially, what they do is that they, for sub-AdS scales, they can argue that the n is in AdS5 plus S5 at least, they can argue that the n equal to 4 theory reduces to matrix quantum mechanics. This is essentially also what I said in the very beginning, that if you holographically normalize all the way to the AdS scale, essentially the coarse graining cell has become as large as the size of the sphere on which the CFT is defined. So you're effectively left with a one-dimensional system, quantum mechanics. And well, Berenstein mentions something that he calls submatrix deconfinement, and the other authors use eigenvalue emission, but the essential point is that they claim the negative specific heat arises by submatrix of the n by n matrix that that only a submatrix is excited in the full n×n matrix. And this sort of resonates, a smaller matrix resonates with a smaller symmetric product. And it's a wild speculation, but perhaps this coordinate transformation that we use to relate ADS-D to ADS-free might be some, is related to an inversion, or it's done by an inversion of radial coordinates. So perhaps there is some version of T-duality that would relate this CFT2 language to the matrix quantum mechanical description that other authors have used. And finally, there has been recent work by Dionysios Aninos and Diego Hofmann, which they have termed world-length holography. They have also reasons to expect this reversal of the UV and IR correspondence in the Sitter static patch. And their work is way more explicit, so it would be interesting to see if either work can shed light. So yeah, I think that's what I have to say. Thanks, Lisa.
Any further questions for Sam?
So if I consider, say, enable 4 and just the usual story in ADS5 process 5, when I change the string coupling, so 0 and small string coupling, there is no sub-ADS locality, and then it's from coupling it emerges. Right. So how does it fit? So the picture is just you have this cell, and this cell, I guess, is just there is ADS scale, and then you change the string scale, and it's make it very small.
Yeah.
If the locality emerges,
Yeah.
how does this sort of usual string picture connect to this thing maybe?
Yeah, so I think a version of that question is asked before. I think the question of sub-ADS locality from the CFT point of view, it should be possible to ask that question from the full CFT point of view.
Yeah.
However, what I'm considering is actually not a description of sub-ADS in terms of the original CFT, but I'm thinking of a description that should be there also of a holographic quantum system that lives on an interior string. So this description should also be exist within the full CFT. But I'm interested in a different holographic quantum system that only describes an interior volume, and which can be obtained by this coarse graining transformation of the original CFT. And the reason why I'm interested in that is because it's this holographic quantum, this coarse grained, whatever holographic quantum system that could teach us lessons about other spacetimes, whereas the CFT, it lives at the boundary of AES, and it's not at all clear that this should also be related to holographic descriptions of these other Minkowski or de Sitter spacetime. That's you can ask questions about sub-ADS differently in the CFT. But I'm interested in the description of the holographic quantum system that's fully coarse-grained, that only contains information about sub-ADS.
But would you expect that even to define this thing, you already need some kind of sub-ADS locality? For example, let me take a free field.
Yeah.
How would you do this? The ADS is so non-local. What is, not really sure what does it mean to have a picture of ADS size in this case. I mean, if the space-time in the theory is very non-local, to what extent it's a well-defined phenomenon?
So I think maybe I should have said that I'm only considering this specific limit that actually the semi-classical
further questions? Okay, then thanks, Sam, again.